With that, Susanna, I'll turn it over to you.
Okay, so
And you should be able to share screen.
yes, share screen. So does it work in this way? Can you see the screen?
We see the screen, but it's not in slide
No,
mode.
no. In fact, do you prefer me to put the
It's
slideshow?
completely up to you.
Well, in case, if you don't mind, I would keep this
It's fine.
this way so that I have a little more um, uh, help from the when presenting one slide, I can see what I have in the next one.
No worries. Whatever is comfortable for you.
Reminds me of what I'm going to forget possibly. so shall I start or would you prefer to wait a little more? Tell me.
Yes, go ahead, please. It's
Okay.
6 minutes after, so.
Okay. So thank you very much for this opportunity to present the work we carry on in Padova with my group in my lab. Thank you for your introduction, George. And I go immediately to an outline of the presentation. So I will briefly introduce the place where we work in Padova, Italy, where we have a device, RFX device, devoted mainly to reverse field pinch studies. This configuration, which is an alternative one, say. The reverse field pinch placed since its very beginning several historical puzzles, and I will briefly mention the self-reversal and the quiescent regime emergence in the Zeta machine in the 50s. I will introduce a toy model for intuitive description, which was first sketched at the time of the first observations in the 50s, 60s, and which we developed furthermore in recent times in the modern era since the 90s. I will present a survey of the experimental facts just to give an overview. And in fact, it was anticipated by 3D modeling that in going to high current experiments, we could observe a helical self-organization emerging, which is seen in our experiments. And then I will enter into the description of the 3D nonlinear modeling, so the numerical model, the equations, we can see the transition to helical regimes. This transition is ruled by the product of resistivity and viscosity, which is well casted in the Hartmann number, dimensionless parameter. We will see that a key role is played by the possibility to allow by a finite value for the radiomagnetic field, what we call a magnetic perturbation, a seed-edge magnetic perturbation in the domain. And so going toward the realistic boundary conditions, since in our experiment we don't have an ideal shell enclosing the plasma, but rather we have a more complicated situations as we shall see later on. Finally, I will describe the magnetic chaos healing effect which occur when we have the helical structure forming. And I will briefly mention a recent development in order to detect finer structures in the magnetic topology, so-called Lagrangian coherent structures, which are able to provide a barrier to the magnetic field line wandering even in regions characterized by a chaotic quality. So briefly, this is an aerial view of the place where I work with the Consortium RFX. This is hosted in the National Research Council research area in Padova. The area is rather close to downtown. Here there is the Palazzo della Ragione, a medieval town hall, and here or there we have the historical site of the Padova University. Consortium RFX is involved in presently the major enterprise is the development of the neutral beam test facility for ITER, and in particular the negative ion source SPIDER has started operation, is now working rather intensively. But historically, the lab started in order to study the toroidal magnetic confinement of hot plasmas, in particular of the reverse field pinch configuration. And we have the RFX device in these buildings. Partners of this enterprise in reverse field pinch studies are found in USA, as you probably know, in Madison, with the Madison Symmetric Torus colleagues, and then smaller machines are also in Sweden, Japan, and a new one is going to be developed in China. Zooming inside the buildings, this is the machine hall. The toroidal chamber surrounded by several coils and mechanical structures, and in particular what the physicists like most, a set of diagnostics. Some of the most evident, the largest one are here highlighted. The soft X-ray tomography, Thomson scattering, reflectometer, interferometer, and also the tool of pellet injector. This picture is taken some few years ago and relates to the setting called RFX-mod, in which we removed the thick shell, introducing a thin shell, so a more less ideal boundary. The previous machine was more similar to the Madison Symmetric Torus. And now the device, we are in a shutdown, waiting for a renewal of the machine, in which we removed also the vacuum chamber, so bringing the plasma closer to the thin shell and the feedback coil systems. We shall see something more later on. Inside this structure, I prepared for thinking of possibly students who are not familiar, also from other fields of the physics. So inside this structure, we have a vacuum chamber in which we puff the gas initially. This chamber is embedded in a system of toroidal magnetic field coils, like you see here. These are exactly the ones used in RFX device. And then we have a system of poloidal magnetic field coils which induce the plasma current. By given a certain toroidal flux, you push to high values the plasma current, like we do in reverse field pinch at variance with the tokamak, in which plasma current is kept to much lower levels with respect to the toroidal magnetic field. And in so doing, in pushing the plasma current, we end up with a magnetic field radial profiles which look like the ones depicted here. you see that the toroidal magnetic field displays this reversal of the sign toward the edge. And then we have the poloidal magnetic field, which is of the similar amplitude as the toroidal one. That means that the plasma current, in fact, provides a significant amount of the confinement magnetic field. As every pinch, the basis of the confinement comes from a self-squeezing effect due to the plasma, to the current flowing in the plasma. This current tends to pinch itself as a well-known effect. As I mentioned in the presentation before, right from its origin, some puzzling issues arose, and in fact this reversal was unexpected, totally unexpected, and it was unexpected also the associated quiescent regime which appeared together. So this is a picture taken from historical papers, and in particular providing material from the Zeta machine, which was in UK. Toward the end of the 50s, they discovered, pushing to a high value of the plasma current above a certain threshold, they discovered this improved stability regime which accompanies the self-reversal of the magnetic field. So this was puzzling during quite a number of years and possibly a couple of decades. And I'm going here to introduce a toy model for an intuitive description of this phenomenology. This is a kind of lumped current skeleton for the 3D magnetofluid modeling. And this toy model was, in fact, introduced since the beginning of the story. It didn't get much success, but we find it very useful, and it has been further elaborated later on in our group. Now, this simple schematic description requires a cylindrical flux conserver, as you see here. You think of a current carrying wire placed on the axis of this cylinder, which conserve the toroidal flux. You can see easily that this configuration is kink unstable, in that any small kinking of the wire would bring the current in the wire to flow in a parallel direction with respect to the current which provides the toroidal flux in the ideal shell. So the current in the wire, the current in the shell would attract each other, and the process would get unstable, bringing an increase of this deformation, which by conservation of the total flux would increase the flux in the core, but decrease a little bit the toroidal field external to the wire by solenoidal effect on the wire itself. Then the process saturates if the toroidal field, or in other words, the shell current is not too large, saturates when this dynamics would force a reversal of the current in the shell, so that the two currents would not attract anymore. Of course, if the current in the wire is too low with respect to the toroidal flux or to the current in the shell, you cannot reach this condition, and then the wire would definitely slam into the shell of this cylinder, which could perhaps mimic a disruption of the system. So now we go to, after this simple description of the self-reversal, we get into the modern era. In particular, I would provide this survey of the experimental effects observed in our more recent experiments. And in particular, the emerging of this helical self-organization was somehow anticipated by 3D nonlinear modeling, as we shall see. But let's start with an overview of the experimental behavior. So this is a pictorial overview of the situation. When in RFX-mod we go to high plasma currents, more or less above 1 megaamp, this operation requires some advanced scheme for mode control in terms by using a rather rich system of feedback coil which covers entirely the toroidal chamber. And by developing this kind of feedback schemes, we can normally normally run discharges with plasma current up to 1.7, but even 2 megampere were achieved, and get electron temperatures about 1 keV or more. When we go, as I mentioned, above certain threshold in plasma current, the system gets a clean helical structure, as you see depicted here, and which corresponds to a modification in the MHD spectrum. The modes are recognized as resistive king modes in MHD modeling, and the spectrum gets this specific shape in which one single mode gets the dominant, becomes the dominant one. Anticipating a little bit the modeling understanding we have in MHD, when we have regimes, multiple helicity, we call regimes with several multiple modes taking play in the dynamics with a rather ordered structure like this one. If you have a look to the Poincaré plot obtained from the simulations, you can see that we expect a rather large part of the domain. You see this is a toroidal section like sketched here. A larger part of the domain which gets chaotic. Only a rather robust chain of islands in the edge, in correspondence of the reversal radius, remain conserved in this situation. And this is also some specific feature of the reversal pinch. But when we go in simulations, in this case, we can get even pure single helical ohmic equilibrium. And in this case, in cylindrical approximation, we can obtain perfectly conserved magnetic surfaces, helical magnetic surfaces, as you can see depicted here. And this has something to do, we believe, with what we observe in our experiment. And in fact, back to the experimental survey, we started to observe this kind of helical pattern emergence in the late 90s with the old RFX machine. Afterwards, we could share this kind of research with our partners, colleagues in the other machine in Sweden. No, this is Japan, in Madison, USA, and in Sweden with T2R machine. And in fact, regimes with this quasi-helical nature could be in fact observed even in older databases, but they were not really considered as interesting features, despite their rather significant presence. More recently, also in the machine in Japan and also in the new machine in China have been detected similar occurrence. In our machine in Padova, this is a typical picture we have with the plasma current, which can last up to more or less half a second. This is one case of deuterium discharge at 1.5 megaamp. You see this is a dominant mode which in effect dominates during the whole of the discharge, apart from some relaxation to multiple helicity case. In green here there are the sum of the secondary modes. This is one example of the typical discharge we have above a certain plasma current in RFX. Here you can get an idea of the statistical robustness of the process. In fact, you can see several large number of points, each one is one discharge. By varying the plasma current, you can see that the persistence of the helical regime, or the quasi-helical regimes, increases significantly in going to higher plasma current. A similar on a statistical basis has been compared successfully in the Madison experiment, and we have some documentation published. In Padova, and this is seen in Padova, in fact, similar diagnosis has not been obtained, has not been found in Madison. During the formation of the helical regime, we observed electron temperature profiles which feature such steep gradients in this around the middle of the radius. And you can see the difference with respect to low current discharges, in which the profile is rather flat. This kind of profile also corresponded to a thermalization of the plasma on the helical flux surfaces obtained in terms of the dominant mode. So this is rather, it looks like a ohmic helical equilibrium. Just to mention a few features, perhaps for those who are already familiar in the talk about the discussions like this, but I don't enter too much into detail. We could observe that the barrier foot, this point where the steep gradient starts, are very well correlated with the place in which the knee, the vanishing magnetic shear location, is detected in the experiment. An additional observation is that this kind of barrier, in fact, is not completely robust. It has a dynamical behavior which is still under investigation. These are the last studies, but we are longing to have new data from the new experiment in 1 year or so. Also, an impurity screening effect is observed. These are data from our spectroscopic colleagues during experimental tests with adopting a laser blow-off of tungsten tile in a quasi-helical regime, they find that the tungsten remains rather well confined in the edge of the plasma. And also in this other case, these are one-dimensional simulation, similar experiments. You see that when we have a quasi-helical regime, this barrier is even stronger, barrier to the contamination of the core by impurities. Finally, another couple of examples to show that this kind of dynamics is sensitive also to the isotopic effect. And in fact, both the persistence and the electron temperature and values improve when we run deuterium discharges. So this was the survey of the experimental facts, and I'm going now to enter the 3D nonlinear MHD modeling of this story to interpret what we observe in the experiment. So we deal with a simple visco-resistive approximation. We have the induction equation here with the resistive term which appears as a result of a simple Ohm's law to express the electric field. We have the momentum equation here. You see that there is a very simple reduction of the stress tensor, and we do have a simple viscous scalar viscous term. We neglected the reaction in the dynamics by pressure gradients or revolution of the plasma density. So we have these two-dimensionless parameters which qualifies the model. Concerning numerical aspects, we adopt a finite difference scheme for the radial coordinate. We have spectral formulation for the poloidal and toroidal periodic coordinates, and we have a predictor corrector and a semi-implicit scheme for time advancement. As I mentioned, we adopt a cylindrical approximation with an aspect ratio which is very close to the RFX at our machine. Concerning the typical boundary conditions, we do keep a constant magnetic toroidal flux. We keep a constant loop voltage, a constant applied electric field, which provides a constant current, more or less. Then for the Fourier components, we can opt among different possibilities. Either we use an ideal boundary, or we apply a fixed radial magnetic field on a selected mode at the edge, which we call magnetic perturbation, with amplitude similar to what we have in experiments. This is going to mimic very schematically experimental configuration. And then recent developments in order to achieve a much finer, much closer description, realistic description of the experimental boundaries. We do have also the possibility to include a thin shell and a vacuum layer inside the ideal wall. The velocities is a no-slip condition. Given this boundary condition, when we choose the initial condition, which is normally a non-reversed pinch configuration, the initial condition define the toroidal flux, which is conserved during the simulation, and the toroidal current. Let me introduce the Hallman number, since I mentioned that since the very beginning, early studies in the 90s, it was empirically clear that what matters is the product of resistivity and viscosity. And in fact, if you rescale the temporal coordinate, the temporal variable in this way, as was done previously in the case of linear stability studies. If you rescale the temporal variable, you rescale the set of the two equations, you get a form like this, in which you see that whenever you can forget about this term, either because you neglect the inertia term or you have a very large magnetic prime number, you get that the Hartmann number, that is the product of resistivity and viscosity, decide totally the dynamics of the system. And in fact, this is what we observe. So we are going in the next slide to see the transition to helical regimes, which appears as a continuous transition ruled by the Hartmann number. In the slide, we will plot the time averaged m equals 0 mode energy, which is the order parameter. In fact, n equals 0 modes are non-linearly driven by the m equal 1 modes. And then we plot this quantity versus the Hartmann number for a rather significant number of simulations. So this is the kind of transition diagram we get. The points are several, each one gives the average of the m equals 0 modes along one simulation. This is only one example, but we have by now very many simulations at hand. This is also the case for a pinch parameter, which is proportional to the ratio of current over toroidal flux, which resemble the usual choice in experiments. And you see that the different symbols correspond to different choices of the resistivity and viscosity, but you see that if we plot against the Hartmann number, the different couples lie on the same curve. So it is H which decides the regime. And in particular, when we have high values for the m equals 0 modes, we get the multiple helicity, multiple modes dynamics. When the m equals 0 modes energy decreases, we get quasi-helical, single helical regime. And at the extreme, if we go to much lower values of the Hartmann number, which means very dissipative systems, we fall down into pure single helical cases, which tends to achieve a vanishing amplitude of the m equals 0 modes, which here I plot with a finite conventional value just for practical purposes, given this logarithmic scale. So this is rather old, let's say, results, but we, in time passing, we enlarged, we extended the studies. In particular, we went to larger value of the Hartmann number, in particular lowering the dissipation, so which means also decrease the time step of the computation. So with increasing computer power, we could afford to enlarge this domain of research. And also we introduced this seed magnetic perturbation in the edge. So you see here in this picture the shadowed the same region which I was discussing before. And by enlarging the domain of the cases, we can see that in fact the m equals 0 modes, by decreasing dissipation, their energy decrease. This is something interesting, because just by this information, since you see that we have quasi-single helical regimes here with this amplitude, we can hope to get here too. And in fact, this is what I'm going to show you in the next slide. but you can see more easily what happens by inspection of the n=1 modes. And here you see the amplitude of the largest n=1 mode in the simulation. And you see that the seeded mode is significantly boosted by the application of the seed perturbation in the edge. So by increasing the Hartmann number and including a seed magnetic perturbation finite radial magnetic field in the edge, we see that the quasi single helical regime appears very clearly. So now I'm going to show this little more in detail the dynamic regimes, giving examples of temporal behavior. As I told you, we start with a non-reversed configuration. Then the modes get excited, and then after a full 3D window, dynamic window, you get one mode. This is a pure singularity with only one single mode and its harmonics present in the simulation. This kind of this is an ohmic, an helical ohmic equilibrium, and in fact we get in this case magnetic flux surface is very purely conserved, which looks like this. In this case we get a helical pinch velocity which accompanies this helical deformation, and which is a drift velocity induced by the electrostatic potential. And as I mentioned before, I think that you can easily convene that there is a rather similarity between the kinked white toy model and this visco-resistive solution simplified in our case. But if we, after seeing, well, let me recall that this kind of behavior was observed early in the 90s, making the people to consider that this pure helical ohmic equilibrium could appear also in a fully three-dimensional situation. And at the beginning, they were regarded just as an academic, theoretical occasion. But in fact, afterwards, after 10 years, the experiments started to show the emergence of this helical structure, refined one. But remaining on the simulation side, if we lower the dissipation, what happens is that we get the typical so-called RFP sawtoothing cycle with the value of the toroidal magnetic field at the edge of the reversal parameter, or the safety factor in the edge if you want, which is showing the cyclic drops, and where we have several modes which participate in the dynamics. But as I showed you in the transition diagrams, if with the same physical parameter as in this case, we just add a magnetic perturbation in the edge, we can see that the seeded mode gets the dominant one and features a behavior very similar to the experimental situations. Let me note that the amplitude of the secondary modes, the ones which disturb the pure helical regime, decreases with the Lundquist or the inverse resistivity, and also with the Hartmann number. And this makes the threshold amplitude for the magnetic perturbation lower in order to excite the helical, the boost of the selected mode. Let me also mention that with respect to experimental estimates of the Lundquist and Hartmann number, dimensionless parameter, we have a very strong correlation with the plasma current for both the Lundquist number and the Hartmann number. This is one last example by using the boundary condition approaching the experimental situation in which we have okay, an ideal wall, but the presence of the vacuum layer and in a thin resistive shell inside. In this way, even without a magnetic perturbation chosen from external means, we can get the dominance of the 1,7 mode as it is observed in RFX machine. Let me very quickly, because I see that time is passing. In passing, I would like to mention some of the features of these typical relaxation reconnection cycles. In particular, the fact that we see magnetic into kinetic energy conversion, we see current sheaths formation, we can observe the phenomenon of mode phase locking, that is a toroidal collapse of the helix, and also the excitation of Alfvén waves, which are the most simple waves in LHD. So magnetic into kinetic energy conversion, you see here the cycle of the reference quantity, the reversal parameter. Here you again can see the behavior of the dominant mode amplitude. This is the total magnetic energy varying in time. And here you can see that at the magnetic energy drop, we get this abrupt increase of the kinetic energy. For those who are familiar with this kind of discussions, plotted here, there is also the magnetic energy and magnetic elicited dissipation rates, but I don't enter into this aspect. Concerning current sheaths formation, here you see a one-dimensional radial profiles of the current, of the parallel current along a diameter, indeed, and this is the mean profile, but you see that the total current profile shows these significant peaks, very localized peaks, which can be identified also in this 2D contour plot on a toroidal section, and that you can see highlighted also here in blue and red in this three-dimensional rendering, let's say. Concerning the mode phase locking, during the cycle, in correspondence of the anticipating the crash, the relaxation of the cyclical relaxation, by looking at the mode phases, you can see that they tend to align, and this corresponds to the localized bulging of the helix, which collapse at a certain toroidal location. Let me recall the toy model, which once again we find very nice to easily, intuitively describe what happens. You can think of the wire, kinked wire. You can imagine in the winding that we have a sequence of contiguous coils which attract each other. So the system can be easily thought to be prone to a slink instability, which provides this localized collapse. So similarly to what we observe both in experiment and in modeling. Finally, we have the recently realized that during these events, strong events, we can detect the excitation of Alven waves. Particular here you see the power spectrum during this temporal window with very definite frequencies getting excited. Here in the radial coordinate you see the distribution which compares the approximate analytic solutions with the spectrum obtained in computation, and this allows us to recognize these waves as global Van Allen modes, and the first in particular gets more excited, the first compressional Alven waves. These kind of observations were also previously detected in our experiment. How to understand the transport barrier observed in RFX-mod? Well, I mentioned that in modeling we get these two extreme situations with a rather large chaotic domain on the one hand, and this theoretical pure single helical ohmic equilibrium with perfectly conserved surfaces which exist only in cylindrical approximation, obviously. But in the real situation, still to say the truth in a cylindrical approximation, but in the realistic condition we can see an intermediate condition in which during the typical dynamical behavior of the mode, in particular during one of the cycle of the dominance of the QSH cycle, we can observe the presence of well-conserved helical magnetic surfaces in the core. You see that they increase during when the amplitude of the mode increases, and finally during the relaxation they are completely lost indeed. I do not enter into the description of the relationship with the safety factor profile, but in case someone is interested, might perhaps be discussed later. What happens is that getting inspiration by several numerical simulation and topological analysis we did in the past, we realized that when a non-resonant helical regimes obtained by the increase in amplitude of a non-resonant mode can be achieved, they are more robust with respect to the magnetic chaos development. And in fact, since now we understood that we can in simulation use a magnetic perturbation to excite some mode, we tried to generate artificially, say, a condition in which a non-resonant mode dominate our numerical discharge. And in fact, this is very easy to do. It does not work with any choice of the mode, but I don't enter more in this aspect. And in fact, by in this example, for example, stimulating a non-resonant helical regime, we see that we get somewhat larger conserved magnetic surfaces domain. And even when several modes come into play during the smaller relaxation, which also in this case occurs, but in fact, even with other modes appearing, we can see that conserved surfaces still remain, so are never lost. In this case, you see that for those who are interested, the helical Q profile is monotonous. To conclude, let me mention that we, in collaboration with colleagues in Torino and in Pisa, we started the study of Lagrangian coherent structures detection. They are finer structures in the topology which provide a barrier to the wandering of magnetic field lines, even when you are dealing with a chaotic domain. We plan to develop this kind of study also on the experimental data, but once again, remaining on the numerical side, in fact, we could observe the formation, the presence of such, let me say, quasi-surfaces, providing an additional barrier to the wandering of the magnetic field lines. We could find these kind of structures nearby the perfectly conserved magnetic surfaces, like might be expected in terms of the KAM theorem, providing the presence of Cantor-I close to the perfectly conserved integrable magnetic surface. So, the possibility to convey the experimental discharge toward these new helical solutions, non-resonant helical regime, has been proposed also in our machine, and in fact, this is the last slide, and in fact, the test worked rather well, and this is one example of our expertise in simulation, driving the simulation starting from the excitation of a non-resonant helical regimes to another helical regime dominated by a mode which instead resonate more in the core, and then the case with a mode which usually dominate in the experiment. In RFX-mod, with our experimental colleagues, we could obtain a very similar behavior of the discharges. So this was just to, and we are, as I will conclude now with a summary, we could study the helical self-organization which characterizes the relative pinch. The experiments show the formation of thermal and impurity particle barriers. 3D nonlinear MHD shows magnetic chaos healing and hidden coherent structures, Lagrangian coherent structures. New global helical regimes are stimulated by seed magnetic perturbation has been suggested by the studies in MHD and have been in effect obtained in RFX-mod. Where the non-resonant mode are expected to provide a more efficient chaos healing. Well, we await for further experiments in the new machine in more or less 1 year. In the new machine, the original vacuum vessel has been removed, so we expect lower secondary modes, so even easier possibility to excite the helical regime. This is, of course, because we expect this because the plasma becomes closer to the conductive shell and to the feedback coils system. So, thank you for your attention. I hope.
Thank you very much, Susanna. Very nice presentation.